Welcome to this specific module called as convolution neural network. If you have to deal with videos, you know for a fact that videos are made up of multiple images. And if you capture images at a rapid pace, that is, if you have frames per second, whatever frames per second, that becomes a video. If you have more frames per second, then the video would become a high definition video, high quality video. And when you have video, usually we split the video into multiple images, frames of images, and each image is again split it into pixels. Each image is going to be split into pixels. And then you analyze the data. You analyze the images. And when it comes to the world of deep learning, we use convolution neural networks to deal with images as well as videos. In the year 2012, when people started with the ImageNet competition, I think in 2010. And they have given towards the competition 10,000 categories. So it was a 10,000 class problem. And there were 1.4 million images. So 1.4 million images and 1,000 categories. And people were expected to build models, machine learning algorithms, such that given a new image, it should be classified as belonging to one of these 1,000 categories. And in the year 2010, in the year 2011, and in the year 2012, etc., people tried traditional machine learning algorithms. The shallow machine learning algorithms are traditional machine learning algorithms. And back then, an algorithm called as support vector machine was becoming famous. It was famous already. Support vector machine. And people were using support vector machine. In the year 2012, along with this support vector machine, people have for the first time tried out deep learning algorithm, and they actually tried out convolution neural network. When they tried this convolution neural network, results were outstanding, amazing. Year on year, when they were trying to bring about improvements were 1%, 2%, etc. And the moment people tried out convolution neural network, improvement was more than 10%. Suddenly, how could someone achieve such a high accuracy? And entire world started looking at neural network. That was a beginning of the era pertaining to neural networks. And since then, people started using only neural network algorithms. If you see in 2012, the guy who is credited for making neural networks famous was called as Alex Krzyzewski. And two other people who were working with the University of Toronto. Right? They were broadly, classified as experts. There are a lot of, image-related problems. And remember one thing, we spoke about first human eye understanding the pixels, then edges, then texton, then motor part and object. That was called as what? Compositionality. Any data, the initial set of layers will capture the low-level information, detailed information like pixels. Then the next set of hidden layers will capture mid-level features. The next set of hidden layers capture high-level information, right? So whatever be the data, it can be images or audio or textual data, doesn't matter. And convolution neural networks can be used for detection, to detect what is there in the image. It can also be used for segmentation, meaning all the humans will be given a specific color, all the trees will be given a different color, so on and so forth. Segmenting. When you have self-driving cars nowadays are predicting who are the people going on the road, what is the probability that these people might come onto the road. Detecting signages, detecting various language characters, pose detection, detecting the human faces, detecting the numbers, number plates on the vehicles, detecting how many whales are there in the ocean, overlaying a map on top of the image, something similar to augmented reality. All these are use cases pertaining to convolution neural network. One additional use case is image captioning. Given an image, give the caption. For example, here, given this image, it says a person riding a motorcycle on a dirt road. That's the entire caption which will be given for this image. That's called as image captioning problem. Now, one question that we need to certainly ask is, why shouldn't we use multi-layered perceptrons on images? What will happen if we use that? Okay, let's understand. Suppose you have Cypher 10 dataset in which you have 10 classes. And each image is of size, color image, each image is of size 32 by 32 by 3, because whenever you have color images, you will have usually red, green, and blue color channels. So when you say 32 by 3, you have 72 weights. So how many neurons will you have? 3072. But today, as we speak, you all have smartphones, a lot of you all. What is the minimum resolution? 1 megapixel, 2 megapixel, 10 megapixel. How much? How many megapixels do you have on your mobile phones? 40 megapixels and all that. Assume I take only 10 megapixels. Means 10 into 10 raised to the power 6 pixels. That means you'll have 10000000 multiplied by 10000000. Why? Because if it's 32 by 32, you multiply. If it's 1 megapixel, or even if you take 1 megapixel, the number of dimensions or the number of weights that your model has to learn will be significantly higher. Why for that case take 32 by 32 image by 3? You have 3072 different neurons. Even if you connect it to a single neuron, how many weights your model has to learn? 3072. If you take 1 megapixel color image, then it'll be 1 million into 1 million into 3. Those many weights your model has to learn. Just imagine the kind of load that would be there on your computer. So if you end up using MLP, it'll be very costly affair because it has to learn a lot of weights and it take huge amount of time. And also, if you have, say, in your hidden layer 5 neurons, all these, if it is 32 by 32 by 3, all these 3072 neurons will be connected to this neuron. All the 3072 neurons will be connected to this. All the 3072 will be connected to this separately, and to this. So that means if I have an image, if I have face of a person here, then rather than focusing on this, all the other pixels will be taken. Because all these pixels would be connected to each and every neuron. So in some sense, global patterns will be captured. When you use MLP on images, global patterns, meaning whatever you have in the image, apart from the face, everything else also will be captured. But maybe face is more important in the facial recognition, image. Face is more important. So there should be an algorithm which will actually just probably deal with patches. This patch of image, this patch of image, this patch and this patch. And in this patch, you'll have more information. Right. Okay. And this full connectivity, right? Every neuron connected to every other neuron is wasteful of resources. And when every neuron is connected to every other neuron, your model might also overfit. Hence, people came up with a new architecture, which is called as convolution neural network. Within convolution neural network, you'll have a concept called as filters. Like we have hidden layers, here we have filters. Filter is nothing but a hidden layer. If you say that you have an image which is of size 5 by 5, 5 by 5 means you'll have how many pixels? 25 pixels. And if I apply a filter of size 3 by 3, filter means hidden layer. 3 by 3 means 9. And say randomly some weights are assigned. Randomly weights are assigned in this way. All these are weights which are randomly assigned. I'm giving some numbers. Now, if you take this and apply on this image, applying is called as convolving. Like you have addition, deletion, subtraction, multiplication, etc. You have something called as convolution. It's a math operation which is performed on images. Addition is a mathematical operation, right? Adding two numbers. It's a math operation on a similar line. Now you take a filter and convolve it on the image. So when you take this and when you convolve it on this patch, you'll be multiplying. In this 5 by 5 image, these are the values that you have: 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1 in this way. Assume that you have data in this manner. When you convolve it on this patch, you do a cross multiplication. 1 into 1 plus 0 into 1 plus 1 into 1 plus 0 into 0 plus 1 into 1 plus 0 into 1 plus 1 into 0 plus 0 into 0 plus 1 into 1. When you do that entire calculation, when you add the values, you get 4. That is going to be your central pixel. Okay. So you're trying to apply this on this so that you take the neighboring pixels also and get value for the central pixel. If you have 3 by 3, can I apply it here like this? You cannot, because here the pixels are not there. Only if you apply on this patch, you get the value for this. But you cannot apply this filter on this patch because you don't have the pixels here. So hence, the border pixels will be gone. You cannot get anything pertaining to the border pixels. Okay. Then if you apply it one stride at a time, by default, You take one stride at a time. One stride means move it by 1 pixel. Then you apply on this. Then 1 into 1 plus 0 into 1 plus 1 into 0 plus 0 into 1 plus 1 into 1 plus 0 into 1 plus 1 into 0 plus 0 into 1 plus 1 into 1. When you do that calculation, you get the central pixel value. That would be this. Then move it by one stride. One stride means one step. So it will come and get applied to you. Then again, 1 into 1, 0 into 0, you add all that, then you get the central pixel value. That would be this. Then again, stride it by 1. Stride 1 means this time it will go and apply here. Then multiply all of these values with all of these values and add, you get the central pixel value, which is this. Then move it by stride equal to 1. You apply on this. Then you get the central pixel value. Then stride by 1, and then you get this central pixel value. Then stride it by 1. Then you get this central pixel value, this central pixel value, this central pixel value, right? Since you cannot calculate those values for the bordering pixels, you will not have anything for this, 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 or this. You can only calculate values for this. Hence, you get a result. When you convolve the filter on the image, you get a 3x3 output. This 3x3 is called as a convolved feature. Feature means input, your data. Some feature will be extracted. Now, we discussed that you have these 9 weights. These are the same 9 weights which get applied on every patch. That means if you want this value, so what do? You take, when you apply on this patch, this orange patch, first 3 rows, then fourth, fifth, first 3 columns, first these 2 are ignored. Then you go to the next. Again, you have 3. Then these 2 are ignored. Then you go to this. Then these 2 are ignored. So these are the 9 weights, which are 101, 010, and then 101. Now, if you apply on this patch, this, then these 2 are ignored. So these 3 are taken. Then these 2 are ignored. Then you go ahead with these. Again, the weights will be the same. 101, 010, etc. So weights are getting shared. The same weights are getting shared across. Same 9 weights are applied across the image. And are you applying on the entire image? No, you are applying only on local regions. So you're not wasting the resources. So weights are shared. Local, since you're applying on patches of the image, local features are getting extracted. Get the values here. Okay. So if you have an image 32 by 32 by 3, if you apply a 5 by 5 filter, forget about 3. Then automatically this 3 also will be taken, because in the image here you have 3. That is called as depth. Depth is number of color channels. In the input, it is called as number of color channels, like red channel, green channel, and blue channel. Those 3 channels are the values that you see here, 3. When you convolve this filter on this, what do you think will be the dimension of the output? Yeah. Can someone let me know? What will be the dimension of the output? If you're finding it difficult, remember that if you have 32 by 32 and if you apply 5 by 5, on this patch 5 by 5, you get the central pixel. Can I apply it on this? Cannot. To get this pixel, I need to apply here. I cannot. To get this pixel, I need to apply it here. That also I cannot, right? So 2 pixels here, 2 pixels there won't be calculated, but it's difficult, I understand. So I'll give you a formula to calculate the same. I'll give you the formula to calculate the same. First thing, even before I give you the formula, is that if you have an image, if you're applying a filter, convolving a filter, then the output that you get would be called as an activation map or a response map. Activation map or a response map or a feature map. All these three mean the same. These are nothing but features that are learned. And if you apply one filter, you get 28 by 28 by 1. If you apply 5 by 5 filter on 32 by 32, you get the output which will be 28 by 28. I'll show you the formula. If you apply 6 5 by 5 filters, then you'll get 28 by 28 into 6. So the dimension here will become 28 by 28 by 6. Now on this 28 by 28 by 6, if you say, let me apply a 5 by 5 filter, it will automatically take 6 because you have 6 here. And if you're applying 10 such filters, the dimension, since you are applying 5 by 5 on 28 by 28 image, the dimension will be 24 by 24. Since you are applying 10, you get 10. So on and so forth. Okay. So typically this is how it looks like. You take an image, supply it to your convolution neural network, where you'll have convolution layers, activation function, convolution layer, activation functions. Usually we use ReLU, convolution layer, ReLU activation function, pool, ReLU, pool. This is a typical sequence, and then you give the data to your fully connected network for classifying the output. Don't worry, I'll explain in detail. Now, first of all, even before I get, if you have n by n image, that is 32 by 32 image, and if you apply a filter of size 5 by 5, what will be the dimension of the output? This was a question. Formula is n minus f by stride plus 1. What is n here? 32 by 32. What is f here? 5 by 5. Divided by stride will be usually 1 plus 1. So what is n? 32. 32 minus f is 5. Stride is 1 stride at a time plus 1. So you get 27 plus 1 is 28. That's what we got here also. 28 by 28. 28 by 28. When you apply in 32 by 32, 5 by 5, you get 28 by 28. That's a formula which can be used. Okay, next. If I say stride equal to 2, what would it do? Stride equal to 1 means it will move 1 pixel at a time, 1 pixel at a time, 1 pixel at a time, and 1 pixel at a time. Then 1 pixel at a time, 1 pixel at a time, in that way. However, if we say stride equal to 2, then it will skip 2 pixels. Then again, it will skip these 2 pixels. Then it will skip these 2 pixels. Then again, 2 pixels are skipped. Again, 2 pixels are skipped. In that way, it's going to skip 2 pixels. And then if you have an image which is of size 7 by 7, filter size 3 by 3, if you say stride equal to 2, what would you do? N is 7, so 7 minus F is 3, divided by stride is 2, divided by stride 2, plus 1. So you get 4 by 2 is 2, 2 plus 1 is 3. So you get a 3 by 3 image. If you say stride equal to 3, N is 7, F is 3, stride is 3 plus 1. So this will be 4 by 3 plus 1. 4 by 3 is you get 1.33 plus 1, which is 2.33. The moment you get in decimals, that means that stride is not possible. If the output that you get is in decimals, then that specific stride is not possible. If you have an image, say this is your image. Which is 7 by 7 means you have 7 and 7, 7 by 7. And if you feel that I want my output also to be of same dimension. Now let me ask you this question. If I take a 7 by 7 and if I convolve a filter of size 3 by 3, what will be the dimension of the output? Stride equal to 1. Yeah, then what will be the dimension of output? Sorry. What is the formula? N minus F divided by stride plus 1. N is 7 minus F is 3 divided by stride is 1 plus 1. So how much do you get? 4 plus 1. 5. So output will be 5 by 5. If I say that no, I want output to be 7 by 7 only, then what do you do? Right? So let's understand. Let us understand what we need to do. You just need to pad it. Padding by 1 pixel border. Padding by 1 pixel border means, one second. Okay. 1 pixel here, 1 pixel here, 1 pixel, 1 pixel. Okay. If I add 1 pixel here and 1 pixel here, in total, how many pixels are getting added? 2. So if I say it is 7, now you'll have 9, 7 plus 2. And here if I add 1 pixel and here if I add 1 pixel, 7 plus 2 will be 9. So overall it will be 9 by 9. Okay. So now your input image is becoming, the moment you pad, 9 by 9. Now let's apply this formula. Input image is 9, filter is 3, stride is 1 plus 1. So you get 6 plus 1, 7. So the dimension would be 7 by 7. So input and output will be the same if you pad it by 1 pixel. Should I pad it by 1 pixel or 2 pixels or 3 pixels to get the output which is exactly similar to input? To get the output which is exactly similar to input, Should I pad it by 1 pixel or 2 pixels or 3 pixels, etc.? Depends on various other things, such as your filter size. If I have a filter size of 5 by 5 here instead of 3 by 3, then even if I pad by 1 pixel, I'll not get this. So I need to pad it by 2 pixels. Why? Filter size is this. Formula is f minus 1 by 2. That means if your filter size is 5, 5 minus 1 by 2 is how much? 4 by 2, which is 2. So you need to pad it by 2. Means add 2 pixels here, 2 pixels here, 2 pixels here, 2 pixels there. So surrounded by another layer of pixels. If your filter size is 7, if it is 7 by 7, okay, instead of this, the filter size is 7 by 7, then you know what filter size is 7, right? 7 minus 1 by 2, which is 6 by 2, which is 3. So you need to pad by 3 pixels, surround. Only then will you get your output, which will be 7 by 7. Okay, next thing is if you have 32 by 32 by 3, and if you're applying 10 5 by 5 filters with stride equal to 1 and padding 2, the moment you say padding 2, if you have 32 by 32, 32 by 32, padding by 2 means you add 2 layers of pixels. That means you add 2 pixels and 2 pixels here. So overall it becomes 36. If you add 2 pixels here, 2 pixels here, overall it becomes 36. So now the new dimension will be 36 by 36. And now if you apply a 5 by 5 filter on that, what will happen to the output dimension? This is n by n, this is f by f. What is the formula? N minus f divided by stride plus 1. N is 36 minus f is 5, stride is 1 plus 1. So you get 31 plus 1, 32. So the dimension will be 32 by 32. And since you're applying 10, it will be 32 by 32 by 10. Okay. Next, how many parameters or weights will your model learn? Here, in this, if I say we have a 3 by 3 filter and all of these have weights, these are the same weights which apply on the complete image. Whether your image is 5 by 5 or 25 by 25 doesn't matter. The number of weights that your model will learn would be the same. So number of parameters will not change. Number of parameters is equivalent to the filter size. It does not depend on the image size at all. So if you have 5 by 5 filter, since it's 5 by 5 by 3 because it's a color image, See, if you have 32 by 32 by 3, even if you apply 5 by 5, it will take 5 by 5 by 3. If you consume this 5 by 5 by 3, you get how much? 75. And you'll have one bias. So total you have 76 parameters. And how many such filters are you applying? 10. So 10 into that will be 760. So 760 parameters is what your model is going to learn. This is the same formula, okay? N minus F. Okay, if you do padding, right, you do plus. Okay, if I have a 5 by 5 image, if I do padding by 2, so if I pad by 1, what will be the dimension of the resultant image? Why 6 by 6? I told multiple times. 1 pixel means 1 pixel on this side. And the same 1 pixel will get applied on the other side also, right? 1 pixel here, 1 pixel here, 1 pixel here, 1 pixel here, right? So 2 pixels get added. So this becomes 7 by 7. So 5 plus, if it's 5 by 5, 5 plus 2 times of padding. So if you look at width also would be the same. That is original width. It's like N minus F divided by stride plus 1. Right? This is a formula. All we are doing is N is nothing but width and height. So N minus F by stride plus 1 will give you width. Height minus F by stride plus 1 will give you the height. Okay. Now, when you do padding, you add 2 pixels. When you say padding by 1 to 5 by 5, when you do padding by 1, how many pixels are you adding on both sides? 2 here, 2 here. That is the reason why 2 is multiplied there. Okay, just in case you are interested in this formula. Okay, this is the same. This is also the same thing. Okay. Con ReLU pool. This is a regular combination. Con ReLU pool. Con means convolution layer, then activation function, convolution layer, activation function, then pooling layer. What do you mean by this pooling layer? Pooling layer is going to downsample your image. Downsample means it's going to reduce the size of the image. Assume that this is the size of the image that you have, which is 4 by 4. When you say, let us do a max pooling with 2 by 2 filter, means you apply a 2 by 2 patch. Since you're saying max pooling, you take the maximum value out of these 4. What is the maximum value? Stride by 2 means skip 2 pixels, go here. You can do stride by 1 also. That's your issue. Now, out of all these, since it's max pool, you take the maximum value. What is the max? 8. Then again, stride by 2. So you get here. Then 2 by 2, you have all of these. What is the maximum value here? 3. Then you stride it by 2. What is the maximum value? 4. When you do average pooling, what do you do here? You take average of all these numbers. That would go here. Then you take average of all these numbers that will go here. If you do average pooling. If you do L2 pooling, you take all these numbers, square them first. Take each number, square it, and then take a square root of that. That's called as L2 pooling. Usually people use max pooling. The advantage with pooling is that the size of the image will keep on reducing the moment you keep applying pooling layers. Initially, your complete image, you take all the pixel values. That means low-level details are captured. Then you reduce it. Again, you don't need the entire image. Reduce it. Then take the other features. Then further reduce it. Take the other features. And another thing is, whether your image, maybe your face was like this in one image, maybe your face was like this in another image, maybe your face was like this in another image, completely tilted like this. No matter in which direction your image is, it should still recognize that it is you by looking at your face. Such things are possible the moment you do pooling. So it makes the data invariant to the translation. Translation means whether your image is like this or like this, doesn't matter. Let's say n minus f by stride plus 1, the same formula. Okay. And then fully connected network. All right. What you do is you apply all the, you have your image input layer, then apply a convolution layer, convolution, in which you'll have activation functions, which should be ReLU. Usually when it comes to images, you use ReLU. Then at the end of this, right, at the end of this, you take all these features, how many features you have, all those will be considered as inputs. And you have your output variable, whether this is a car or a truck or an airplane or ship or a horse. Say you have a 5-class problem. So you take all those 5 classes and then you build a model on this, which is a fully connected network. And then whichever class has a maximum probability, that would be the output. So first, on your image, you are applying convolutional base to extract all the features from the images. Once you extract, you take those and supply it to your fully connected network or a dense network or multi-layered perceptron, which we have already spoken about. And then that would do the final predictions. Clear? This was a very, very complicated exercise which Alex Krzyzewski has done in 2012 along with his team. Look at what all experiments they have done. They have taken the input, they have applied 96 11 by 11 filters, tried 4, they didn't do any padding. Then they applied max pool. Normalization is used for it is used as a regularization technique. You know about normalization, right? What is normalization? X minus mean by standard deviation. Oh, sorry, X minus mean by, yeah. But here, the normalization that was applied was standardization. X minus mean by standard deviation. All the weights you have, right? They took all the weights and they've applied this formula. The moment they applied the formula, mean of all these became 0, standard deviation became 1. And they proceeded further with that. So this turns out to be a very good regularization technique. Then they applied 256 5 by 5 filters, then max pool, then norm, then this, so on and so forth. Here until here, it was convolutional base. Then all these would be part of your fully connected network or a dense network. Here, they've also tried out heavy data augmentation. Do we have data augmentation details here? No, I'll talk. Data augmentation means generating more data by using the data that you already have. If you have an image like this, rotate it by 90 degrees clockwise. So how would your image look like? Rotate it by 10 degrees. If you have 1,000 images like this, if you rotate it by 90 degrees, you get another 1,000 images. If you rotate it by only 10 degrees, you get 1,000 degrees. Rotate it by another 20 degrees, 30 degrees. So in that way, what would you be doing? You'll be generating a lot of data, additional data. That is called as data augmentation. Data augmentation techniques are also considered to be regularization techniques. And when it comes to images, people apply data augmentation. Then they use dropout, 50%. What does that mean? If you have a network like this, when you say dropout equal to 50%, 50% of these will be randomly dropped off. 50% of these will be randomly dropped off. For every record, for every row of inputs that you pass through your network, 50% are randomly dropped off. That's called as dropout. And dropout also happens to be a very good regularization technique. Then they tried out various other things. Learning rate value was chosen as 0.001, I think, or 0.01. So on and so forth. Okay. So let us run this Python code. It's taking a while. Okay. This specific function is to import the TensorFlow, okay, as TF. And this line is to check whether you have your GPU or not. It says yes, GPU is available. And I'll stop it. Why run complete thing, right? I'll take these things so that oh, false. False means Kuda. Yep. We don't have a GPU. Let me see. Why we should be having a GPU. Didn't we select? Oh, we didn't select GPU. Okay. Let me select high RAM also. So to run this, come on. Why? Okay. Let me terminate all the sessions. Yeah, look at that. It's saying true, meaning GPU is enabled. Previously, when I run it, it was saying GPU wasn't available. So here, what we are doing is we are importing the required libraries layers and models. We are creating a sequential model in which we are saying, we are creating an empty model and we are saying input will be 28 by 28 by 1. 1 means black and white image, grayscale. 3 means color image. 28 by 28 by 1 would be 784. Then you're applying 32 3 by 3 images, 3 by 3 filters, 3 by 3, 1 filter, 3 by 3, 3 by 3, 3 by 3. How many? 32. And you're using ReLU function as activation function. Then after that, you're coming up with max pool. Pooling layer is used to reduce the size of the image. And also when your image is, invariant, translated, then also it will work well. Then you're adding 64 3 by 3 images with activation function ReLU. Then you are going to add again max pool 2D. Then again you're going to apply convolution layer 64 3 by 3. Finally, you look at model summary. Model summary will explain you how many parameters your model has learned. Pooling layer doesn't have any new parameters, friends. And how many filters are we applying? 32. Size 3 by 3. 3 by 3 means 9. 3 into 3. Plus 1 is bias. So 9 plus 1 is 10. 10 into 32 will be 320. Pooling layers will have no parameters that it will learn. That's how it's calculated. You have these many parameters. How are the number of parameters calculated? That formula is given. Next, you're also coming up with a fully connected network. Here, this is called as convolutional base. And this is called as a fully connected network. Flatten means here, how many do we have? 3 by 3 by 64. Your multi-layered perceptron algorithm, if you supply to it data in this way, it will be confused. Because in the input layer, either have 10, 20, 30, 40, 50, whatever. But if you say 3 by 3 by 64, it's like 3 dimensions. The moment you supply it, it will throw error. It will say, I don't know. I don't understand. Hence, what do? You flatten it. Flatten means you convert 3 dimensions into 1 dimension. How do you convert this 3 dimension into 1 dimension? Just multiply these. When you multiply, how much do you get? 576. And that's what flatten will do. Then you have layers that you're adding, dense layers, 64 ReLU. Why do we have 10 neurons here? We are trying to classify whether the digit is 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. It's a 10 class problem. Since you have multi-class problem, the activation function is softmax. And is that what was available here? If you have more than 2 categories, what is the output layer activation function? And then your loss function should be categorical cross entropy. So here, if you look at this compilation, right? Categorical cross entropy matrix is activated. Same thing that we have done. We are importing the libraries. MNIST dataset is a dataset of handwritten digits, modified National Institute of Standards and Technology, I think. This dataset has grayscale images or black and white images, which are handwritten numbers, 0 until 9. Okay. So you load the data. When you load the data, You have training data inputs, training data output, test data inputs, test data output. You're ensuring that all the images which are of size 28 by 28 by 1 are actually of the same shape, and you have 60,000 such images. You're reshaping it. And then you're converting every image value here, pixel value, to a float value. Why are we doing that? Because your weights that get assigned randomly are float. The inputs that you supply when they are float into float, it will not give any error. Otherwise, integer into float, it will throw error. Weights will be float. You cannot convert them into integers because that's the underlying algorithm that works. Hence, what you're doing is the inputs which are being supplied, you're converting those into float. Why am I dividing the values with 255? Normalizing. Pixel values range from 0 to 255. And if you divide each value with 255, you get 0. If you divide here, you get 1. So you're converting the range which is 0 to 255 to 0 to 1. So that's what we are doing. And we are converting the output variable to one-hot encoding. Why one-hot encoding? To calculate categorical cross entropy. To calculate cross entropy, I need the data in categorical format only. Okay. Once you do all this pre-processing and compile the model, you fit the model. When you train your model on training data, inputs and output. You're saying I want 5 epochs, batch size 64. When I say batch size equal to 64, what gradient descent algorithm are we applying? Gradient descent algorithm. What are the three? Batch gradient descent, stochastic gradient descent, and mini batch SGD. Mini batch stochastic gradient descent. The moment you provide batch size, it's understood that we are talking about mini batch SGD. Once you build your model, you'll have to say use the model to evaluate on the test data. The moment you evaluate, you get two things, loss and accuracy. You get your loss. On similar lines, you can also evaluate your model on the training data, training images, training labels, save it in training loss and train accuracy. Ultimately, you get the values. It's running. It's taking a while, friends, because you're dealing with slightly bigger data set, right? So it's taking 3 seconds per epoch. But if you have powerful GPUs, based on your GPU configuration, it will either run fast or slow. Okay. So your test data accuracy happens to be almost 99%, and your training data accuracy happens to be again 99%. Okay, so yeah, Siraj.
Hello.
Siraj? Yeah.
Yes, sir. Sir, how to visualize this process geometry? Have you shown in convolution this? You shown
Shown
in
it?
that PPT. Convolution that process is convolution process is shown as na.
Yeah. So are you saying that?
How can we see? How can we visualize this?
So
This
if your
image,
question
last
is,
one. This one.
1 second. I'll show you a better version, right? Maybe then you'll understand even better. At least other people will be able to understand better. So our friend's question is, how do I get these kind of visualizations?
Yes,
When I
correct.
apply convolution layers, these things. That is called as visualizing the hidden layers and the hidden representations. It be taught to you as part of your AI and deep learning training. It's not within the scope of our regular training. In AI and deep learning training, that's for PDS students, we teach them. We explain them on how to visualize the activation functions, how to visualize the filters, and how to put a heat map on top of your existing image to figure out which component is getting highlighted. For example, right? If you have a facial recognition system or CCTV camera, okay, and your one algorithm is highlighting the human hand to classify that it's a human, not facial recognition, say whether the person entering the shopping mall is a human or not. And another algorithm is looking at the face to say that you're a human. Which algorithm will you rely? Obviously, the algorithm which is highlighting the human face to classify that this is a human. Right? So after you build the model on your existing images, you put a heat map. It will highlight which portion or which part of the image is getting selected to say whether that is a human or not. Right? All these kind of advanced things and transfer learning techniques you learn as part of our AI and deep learning training. Okay. Any other questions, friends? I think we are well ahead of time. Ask me if you have any questions. I don't intend to start the next thing, which is RNN. Tomorrow at 9, when we start this, probably in 1.5 hours or so, we'll be able to complete RNN. So tomorrow we will take this up. But if you have any questions, ask me now, please. What do you mean by feature engineering? I didn't quite get you, Raju. Yeah, Raju.
Sir, yes, sir. Actually, how can we do feature engineering, especially deep learning for the images?
You don't do any manual feature engineering, Raju, in deep learning. Everything is automatically performed by a deep learning algorithm only, neural networks only. And also the disadvantage, that's the best part. So automatically feature engineering happens. But the flip side of that is that it is black box. What features are extracted, we will not come to know. Okay. The only way out is to probably try and visualize like this and put some effort to understand, hey, probably edges are getting highlighted. Okay. Maybe some kind of blobs, circles are getting highlighted here. Maybe with some difficulty, you'll be able to make out that, but otherwise in deep learning, feature engineering is automated process.
Okay, sir.
Yeah, sure.
Thank you, sir.
Yeah. Any other questions, friends? All right. If you have no questions, then thank you so much. We'll connect tomorrow and take this discussion forward. Tomorrow we'll complete RNN. Once the RNN part is done, for our regular weekend batch students, we have other things like we have to run the code pertaining to naive Bayes, and then we have to get into support vector machine and our regression techniques. Probably next weekend we will be able to complete the training. So I'll stop here.